Assalamualaikum warahmatullahi wabarakatuh. My name is Imran Najmi bin Badri. I am from CS1104, and in this video we are going to take a look and try to answer some questions related to path indirected graphs and basic connective, truth table, and logical equivalence.
My name is Muhammad Ini Hakimi bin Kasim. I am from CS110 and I am from Group 4.
Assalamualaikum. My name is Muhammad Faiz Nur Hakim bin Muhammad Fahman. I am CS110 student and I am from group number 4.
My name is Muhammad Haziq bin Nazri.
For the first question, give an example of a simple path of length 6. So here is the answer. 1, 2, 4, 6, 7, 5, 3.
Now let's look at the next question, which is give an example of a Hamiltonian circuit. If it does not exist, give your reasons. Now, in this graph, a Hamiltonian circuit only exists if it has at least 3 vertices and it passes through each vertex on exactly once. Now, keep in mind that there is no simple rule to determine the existence of a Hamiltonian circuit, and the graphs must be strongly connected in which there is an edge connecting to every pair of vertices in the graph. Now, one Hamiltonian circuit is already shown in the graph. There are several other Hamiltonian circuits possible on this graph, and notice that the circuit only has to visit every vertex once, and it does not need to use every edge. And this circuit could be notated by the sequence of the vertices visited, starting and ending at the same vertex, which is 7, 5, 3, 1, 2, 4, 6, 7. Notice that the same circuit could be written in the reverse order, or starting and ending at a different vertex. Here are some other examples of a Hamiltonian circuit.
So now I'm going to explain about Euler circuit and Euler path. So as you all know that Euler path exists when there is exactly 2 vertices with odd degree. So as you all can see here, for question 4A, April 2011, here is the graph. For vertices 6 and 7, there are exactly 2 vertices with odd degree. So that means for this question, the Euler path exists. So how about for Euler circuit? So based on the definition, Euler circuit does not exist because the vertices have odd degree. So that means Euler circuit only exists when all the vertices have even degree. So because of the vertices number 6 and 7 have odd degree, that means the Euler circuit does not exist. So for question 3 here, it asks does Euler path exist or not? So my answer is an Euler path exists because it has exactly 2 vertices with odd degree, which is vertices number 6 and number 7. So as an example of Euler path, for Euler path, it begins and ends at the different vertices with odd degree. So as you all can see here for the example, I begin at vertex number 7 and ends at vertex number 6, which is both is odd degree. So for the example, it must begins and ends at different vertices but have odd degree. So here is the example of Euler path from vertices 7 to vertex number 5 and vertex number 5 to vertex 3 and then to vertex number 1 and then vertex number 2 and go to vertex number 6 and then vertex number 4 back to vertex number 2 and then go to vertex number 3, next going to vertex number 7 and is going to end at vertex number 6. So that's all for question number 4 April 2011 and about Euler path and also Euler circuit.
So question number 4. Given an example of undirected spanning tree. So for this question, you just need to draw undirected graph like this one. So there is no end for this graph, so there is no like a direction on this graph. That's why make it undirected graph.
For the first question, state the degree for each node. As you can see here, there are 7 nodes. And for each nodes, the first one is A, it have 2 degree, 1 and 2. And for B, it also have 2 degree, 1 and 2. The third one is C, it have third degree. The fourth one is D, it has 4 degree, 1, 2, 3 and 4. The fifth one is E, it have 2 degree. The sixth one is F, it have 3 degree. And the last one is H, it have 2 degree. And the second question, find an Eulerian circuit or Eulerian path. So an Euler path exists because it has exactly 2 vertices with odd degree. As an example, F, E, D, H, F, D, C, A, B, C, which is F, E, D, H, F, D, C, A, B, C. And last one is an Euler circuit does not exist because there are vertices with odd degree.
Start recording. Alright, so right now I'm going to explain about logical equivalence, which is one of the subtopic in topic 5, and I'm going to use June 2012 question 5b as my example for this presentation. Alright, so logical equivalence is about two statements A and B as example. It can be any statements, statement C and D, or statements 1 and 2. So as example, I will use statement A and B because this question also asks about statements A and B. So if statements A and statements B both have a true state is true, that means it is a logically equivalent. So we're going to see about of this question 5, June 2012. So here statement A is says that if today is raining, then I will bring an umbrella, and I will not bring an umbrella. So that means P implies Q and negation of Q. So for statement B, today is not raining, which is negation of P. So here's my truth table. So from this truth table, I get the answer, which is statements A is not logically equivalent to statements B, because here in statement B, I get true for my truth table, but for statements A, I got false. So it is not logically equivalent between statements A and statements B.
So question number 5A. Determine whether or not the following two statements are logically equivalent by using a truth table. So the first thing you need to make a truth table for A, B, C and just put a statement true or false. Then put the logical equivalent in the table and solve the statement given. And then the last one, we just compare two tables and get the statement. So the statement are not logically equivalent.
That's all from us. Thank you for watching and have a good day.